Tonight, we are at 56 minutes, not precisely 24 hours, but close enough for everyday purposes. This rotation creates day and night as different parts of the planet turn toward and away from the sun. At the equator, you are moving at roughly 1040 miles per hour because of this rotation. That's faster than the speed of sound. You don't feel this movement because everything around you, the air, the ground, and the buildings, is traveling at the same speed. But you can observe its effects. That Coriolis effect causes hurricanes to spiral, makes wind patterns curve, and would cause a ball drop from a tall tower to land slightly east of where you might expect. But why does Earth rotate? The answer takes us back about 4.5 billion years to the formation of the solar system. The solar system developed from a cloud of gas and dust known as the solar nebula. This nebula was enormous, stretching across several light years. It was composed mostly of hydrogen and helium left over from the Big Bang, mixed with heavier elements produced by earlier generations of stars that had lived, died, and scattered their remains. This nebula was not motionless, it was moving. Different sections of it had different velocities. Some regions were moving a little faster, some a little slower, some were drifting in one direction, while others moved another way. This is critically important. Across the enormous expanse of interstellar space, you will never find a cloud of gas that is perfectly still, with every part moving in precisely the same direction at exactly the same speed. It simply does not happen. Random turbulence from nearby stars, shock waves created by distant supernova explosions, and gravitational pulls from the passing molecular clouds all create motion and differences in motion. And wherever there are differences in motion, there is angular momentum. Angular momentum is one of the most important ideas in physics. It's the rotational counterpart of ordinary moment. Just as an object moving in a straight line has momentum related to its mass and velocity, a rotating object has angular momentum connected to how quickly it's spinning and how its mass is distributed. The crucial feature of angular momentum is that it is conserved in a closed system with no external torques. The total angular momentum remains constant. This conservation law is just as fundamental as the conservation of energy or ordinary momentum. It's one of the fundamental principles of physics, derived from the symmetry of physical law under rotation. When the solar nebula began collapsing under its own gravity, perhaps triggered by a shock wave from a nearby supernova, it started pulling itself inward. Gas and dust moved toward the center, where gravity was strongest. As the cloud collapsed, something both intuitive and remarkable happened. It began spinning faster. You have seen this if you have ever watched a figure skater. When a skater begins a spin with their arms stretched outward and then pulls those arms close to their body, they rotate faster, much faster. This is not because they are pushing off when their feet are doing something to add energy. It's simply conservation of angular momentum. As the scatter's mass moves closer to the axis of rotation, the rotation speed has to increase in order to keep the total angular momentum constant. The same thing happened with the solar nebula. As it contracted from a diffuse cloud several light years across into a dense region only a few billion miles wide, all that angular momentum became concentrated. The nebula rotated faster and faster, but something else happened as well. The nebula did not collapse into a sphere. Instead, it flattened into a disk. This is a crucial detail that explains so much about the structure of our solar system and planetary systems around other stars. Why did it become a disk? Because of the interaction between gravity, rotation, and collisions. Gravity pulls everything toward the center from all directions, But rotation creates centrifugal effects that resist collapse perpendicular to the axis of rotation. Imagine the nebula rotating like a giant wheel, material attempting to fall toward the center along the rotation axis through the poles encounters very little resistance from the rotation. It can fall directly inward. But material trying to move toward the center perpendicular to the axis through the equator experience rotational motion that prevents it from falling straight inward. Instead, it settles into orbits around the center. At the same time, particles inside the nebula are constantly colliding with one another. Gas molecules bounce into each other while dust grains repeatedly bump together. These collisions smooth out random movements. A particle moving sharply upward away from the plane collides with other particles and gets pushed back down. Another particle moving sharply downward collides and gets pushed back upward. Over millions of collisions, these random vertical movements become damped out. What remains in organized circular motion around the center. The result is a flat disk of material, with everything orbiting in roughly the same direction around a dense central concentration. This disk is called a protoplanetary disk. It's where planets are born. At the center, where density and temperature become highest, hydrogen fusion eventually ignites, creating a star. That's your sun. In the disk surrounding it, dust grains stick together and form larger clumps. Those clumps attract additional material through gravity, growing into plant simals, then protoplants, and eventually full-sized plants. Earth formed through countless collisions between these smaller bodies, and every body collision transferred angular momentum. Imagine two plant simals, each several hundred miles across, traveling along slightly different orbits. They collide but almost never head on. Space is three-dimensional and orbital paths are complicated. The collision happens at any angle away from the center. When one body strikes another off center, it causes the combined object to rotate. It's like hitting a pool ball away from its center with the cue. The ball does not simply travel in a straight line, it spins. Over millions of years, as Earth grew through countless collisions like these, all those contributions of angular momentum accumulated. The result was a planet rotated on its axis. The different directions of that rotation, that tilt of the axis, and even the length of the day were all influenced by the details of those collisions. They are essentially random outcomes of a chaotic press. Earth's axis is tilted 23.5 degrees relative to its orbit around the Sun. That tilt gives us seasons when the northern hemisphere is tilted toward the Sun. It's summer there and winter in the southern hemisphere. 6 months later, the situation is reversed. But why 23.5 degrees specifically? Why not 30 degrees, 15 degrees, or 0? Because what resulted from the particular collisions that formed Earth. A different series of impacts could have produced a different tilt. In fact, there is strong evidence that early in its history, Earth was struck by a Mars-sized object called Thea. This impact was so powerful that it launched a huge amount of material into orbit around Earth. That material eventually came together to form the moon. The impact also likely altered Earth's rotation, possibly creating the current axial tilt, or at least changing it significantly. So, Earth spins because of the angular momentum inherited from the solar nebula and modified through billions of years of collisions during its formation. But Earth's rotation is gradually slowly down, and we can actually measure it. The length of a day is increasing by about 1.7 million seconds per century. That might not like seem much, but over hundreds of millions of years, it becomes significant. Around 4 million years ago, during the Devonian period, when fish were first beginning to move onto land, a day was roughly 25.5 hours long. There was around 410 days in a year instead of 2 days, 30, 365. What's responsible for this slowdown? The moon, specifically tidal function between us and the moon. The moon's gravity pulls on Earth, producing tides in the oceans. The sides of Earth facing the moon experiences a stronger gravitational forces than the side of facing away from it. As a result, water bulges towards the moon and also form a bulge on the opposite side of Earth. As Earth rotates, these tidal bulges attempt to remain alignment with the moon. But friction with the ocean floor and the viscosity of the water itself prevent the bulge from staying perfectly aligned. Earth's rotation drags the tidal bulges slightly ahead of the moon. The moon's gravity then pulls backward on this bulge, producing a torque that gradually slows Earth's rotation. At the same time, according to Newton's third law, Earth also pulls gravitationally on the moon. And because the tidal bulge is positioned ahead of the moon, this gravitational pull has a component in the direction of the moon's orbit. This gives providing it with more orbital energy and causing it to slowly move outward away from Earth. So Earth's rotation is slowing down while the moon is moving further away.
form the rotating solar nebula. As the center of the nebula collapsed to the create of sun, it inherited the angular momentum of the material falling onto it. You might think the sun should be rotating much faster than it actually does. If you took all the angular momentum from the original nebula and concentrated it into an object the size of the sun should rotate once every few hours rather than once. Additionally, the young sun lost angular momentum through its solar wind.